Okay, so welcome everybody. Welcome to all the attendees, and a particular thanks to Igor Tetko and Chris Southan, who are our speakers today. So Igor's going to kick off, and then we'll have Chris take it over from there. Caroline, anything to add before we go ahead?
We invited Igor because, can you hear me?
Yes.
We invited Igor because he's the coordinator of several of the very large EU initiatives in big data, particularly the current one in big data in chemistry. And he also runs the Virtual Computational Chemistry Laboratory and a website called OCHEM, which he's going to tell you all about, which is a collaborative initiative on building models for predicting physicochemical parameters. So I'll leave it to him. I'll hand over to him now. Thanks very much, Igor. Over to you.
Can you hear me well?
Yep, that's great.
Yes.
Okay. So now, so welcome everybody, and thank you for this kind invitation to present our work. And I was asked to speak about basically OCHEM and also put some emphasizes on patents. So I will speak not completely about all physicochemical properties, but more one property, melting point, for which we have recently developed a nice model and published it. So as was mentioned, just see how I can go to next slide. How can I go to here? I have to click. Okay, so I will be speaking about models which we have developed using online chemical database modeling environment. This is a public website. Everybody can go to this website, can create an account, or can just go as a registered user and see what we have developed. So there are about 100 models already published there by different people from my group, from collaborators, from external people. And what is nice is feature of these models, all the models publicly available, can be accessed on the web and used for prediction of new molecules. This is how we do model development on the website. So basically there is a workflow. Users can select data sets, can create training and test set. They can select different descriptors. We have about 24 different packages. After this, they have a possibility to build models, validate them, and to have final model developed and to be used for prediction of new molecules. What are the available models? This is some overview of a few models which are there. The most important ones for physicochemical properties, biological activity, environmental endpoints. And what I will speak today, it will be mainly about water solubility, melting point, and pyrolysis. And basically I will speak about melting point, but water solubility will be applied using one of the equations where melting point is used. So how we did come to this work, what I will present. Especially it's interesting story we have published in 2014 model about melting point predictions, which this work was done together in collaboration with Enamine company in Ukraine. We got data from them, and when we published this model, we were thinking, okay, this model will stay for a long time. It's the biggest published data set, about 47,000 compounds. So we have done a good job, and really this will be staying for a long time as it's one of the biggest models data field. This is data which we had in our model. We had drugs, Bergstrom data set, 277 compounds. We had Bradley, so-called Bradley data set, which had double correlated data with very good quality of melting point data. We had data which we uploaded to OCHEM by different users, about 22,000, and we had a donation of Enamine, who were also collaborators, more than 30,000 compounds. But we deduplicated all sets in this order, so we didn't have any duplications, any duplicated molecules for all data which we had for the model. So what model was developed, and one of the things which we have found there, except the accuracy of model, that majority of melting point data, which are drugs or produced, for example, Enamine company which produces compounds for screening. They have a melting point in the range from 50 to 250 degrees. So this is 90% of all drugs or NMI data have melting point in this region. So basically, if you are developing a model for application drug discovery, it does make sense to concentrate on this region of melting points. And for this region of melting points, our model was able to have accuracy about 33 degrees of Celsius. It's not so high, but this is what we could get from the data. So we developed this model, we made it publicly available, and by chance we had contact with Anthony Williams. He was working with Daniel Lau from Next Small company, and they were interested to see how this model would work for their data. They sent me a couple of a few hundred structures which I predicted, and they say, why not to do something more? Why not to try to see how can we develop model with data mainly from patterns? And this was end of our next work, which was published already this year. And this work was already based on much bigger data set with about 300,000 compounds for melting point and also for pyrolysis for decomposition. So this data, the previous work was just introduction to a bigger study which we have done recently, which I will present now. This is how data look like for a big melting point data set. As you can see, the data which we have used in our previous study, just a small portion, just less than 25% of all data which we could get thanks to access to patents, thanks to the development of technology by a Next Move company which extracted data from patents. Just to show example how the extraction data was performed, I took some examples. So, for example, if we look on the web, we can find in Google.com patents, and there is information about structures which were described in patents. For example, this is just can go to this link. You can find the data there, and one can see that okay, there are some interesting data. If you are, for example, developing melting point model, we could see, okay, maybe we can take some melting point data from here and use them for our studies. And to do this, Next Move developed a nice workflow which is processing such raw data. They take raw patents, they use XML patent representation, they detect paragraphs and headings, experimental sections, and extract information from the patent. This can be reaction data, this can be also physicochemical properties, and for our study we used melting point which were extracted as example of data. This is how the same pattern looks after processing by software from Next Move. You can see that, okay, software identified that there was a structure connected to a melting point. This link was identified and could be extracted and stored in database for offline processing. So this is all the data processed, all patents are processed by Next Move software, and what we got data which we could upload to OCHEM, and also we made them publicly available. This data are downloadable to everybody. So this is how it looks like. We extracted data. In many cases, melting point data had intervals, so we stored also intervals. OCHEM supports intervals. Importantly, we indicated name of molecules. It was always named to structure recognition. We always have names of molecules. We have also information, for example, if there was decomposition, we have additional field indicated the decomposition. Sometimes we had just intervals. This data were stored also as intervals. So this was implementation, and thanks to the software from Next Move, we could get a very big data set of data, melting point data, more than about 500,000 compounds from patents, 173,000 compounds from applications, and of course many of them were duplicates. Sometimes the same data were in different patents. Exact duplicates were eliminated. After this, we also eliminated duplicates for which we had several measurements. in this case, we try to take value, not just to take median, but just to take value which was most close to median, just to have possibility to trace back if there is any question to the one of the patterns where this data was mentioned. And again, we eliminated all duplicates of the previous data sets. So by this procedure, we decreased a number of points to about 275,000, 288,000 coming from patterns, and 50K about coming from previous data. Also, some data were annotated as degradation, so we had about 13,000 data points with degradation data. So we got quite big data sets, as I say, about 275,000 points. And challenge was how to develop models, because it's quite a big data set. And just to show which kind of challenges we have, I show descriptor sets which we have used for software development. So for this modeling, we used different descriptors which are available on OCHEM. Here I show package name and type of descriptors was used, number of descriptors, and also how big was matrix of descriptors versus molecules. So some of descriptors were quite small, like inductive descriptors. For them we had just 54, but some of the descriptors were really huge ones, like print. We had about 700,000 descriptors for different molecules. But what was found, the descriptors were very sparse. So just for one of 7,200 values were on average not zero. And so if you look for this matrix which was produced for multi descriptors was like 205 billion entries. This is a very huge matrix. And in order to support and be able to work with such big data sets, we developed storage of sparse data format in our system. And we were able to proceed with all these descriptors using the same algorithms, the same algorithms. In this case, was used Campbell method, support vector machines, and to analyze them in a similar manner by OCHEM. So this was our setup, and how we develop models. We use so-called comprehensive modeling. Comprehensive modeling allows to use exactly the same protocol. For example, in this case was Largescale with all descriptors and just compare different descriptors how they perform for machine learning methods. So, for example, for all the descriptors we applied Largescale, we could see that some descriptors perform much better. Some descriptors perform much worse, like the most what we have spent time for, multi, they don't perform very well for the dataset. But comprehensive modeling, this is allows us to see in one instance all results, to see it very easily. So we use it, we develop a model. We also found that the best models were not by individual descriptor sets, but the really significant improvement of accuracy could be achieved by consensus modeling when we merge several descriptors. In this case, we for my melting point, we select 5 best descriptors with the lowest prediction errors, and decreased by significantly about 2 degrees for this set. So we have developed models. Now we can look how the models look like. This is a model which was developed with all data, with 270,000 compounds, and the characteristic of this model also can be visualized by anybody who goes to OCHEM website. You can easily find this model, and you can see that we also excluded some outliers points, outlying points. Why these points were excluded, and what could be reasons to exclude them? So the training set was 271,000 compounds, and we excluded about 3,500 compounds as outlying points. Basic idea to exclude compounds came from the initial study which we had done initially with all data. We joined both melting point and degradation pyrolysis data point together. We modeled the data and we found that pyrolysis data points were outliers. They had much worse prediction, so for the second step we separated melting point and pyrolysis point for 2 different sets. But way how we found these outliers was following. We have some model. We can assume that distribution of errors in models is approximately Gaussian. So molecules which have much higher errors as compared to those which can be expected by Gauss distributions, can be considered as outlying points. We did this for initial dataset. We analyzed and we found that many outlying points were really points coming from a periodic dataset. It's not melting point. So we say, okay, we should separate them. But still, once we did the separation, some points were still outlying points, and we also separated them by using the same technique. We look for so-called applicability domain. So for applicability domain, we look how similar molecules is to the training set, and we can calculate average accuracy for some distance to model. So for these compounds, which are quite similar to training sets, we can expect black lines from average error, and this average error for very similar compounds is smaller compared to compounds which are far from datasets, from training datasets. So if we take average, we can calculate standard deviation. We can find compounds which have much higher errors. For example, here we have average error something like 30 degrees or maybe 25 degrees, but some compounds have errors about 400 degrees. So probably this compound, there is something wrong with this compound. Could be experimental error, could be also kind of poor representations of our molecules with descriptors, whatever. But we see this problem. We can easily identify this compound and we can exclude this compound. So once we do this, we can exclude compounds and rebuild model. And these compounds are not limited to the set. They are still present, but we can see that for them we have much worse prediction. And the result is shown after calculation models. Even if we exclude these compounds from the training sets, there are still outlying compounds that could be something wrong with this compound. I will come to this point later, but just to come to this model, how good is model? Well, we can compare model with experimental accuracy. If model is providing similar accuracy to experimental one, we could be quite happy. We were lucky that in data set from patents we had a number of duplicated measurements which were not exact duplicates. We put some like rounding error about 1 degree, and compounds which had error predicted melting point experimental errors more than 1 radius Celsius, we could calculate them as duplicated. We could find about 18,000 pairs, and from this we could estimate experimental accuracy of our data. Since we assume that the same compounds, if you have duplicated measurements, probably, and not exact measurement, probably they came from different experiments. So we did this estimation as a black line, and we could get estimation how well our model predicts and how well it corresponds to the experimental accuracy. And you can see it's very good coincidence. So basically, models, what we have developed, or consensus model, it reproduced experimental error of data which we have estimated, and so basically we achieved what we could achieve best. We could not go better than this model. If you look for the same model, how it works for different data sets, the red one shows patents. Also, it shows for different data sets like Bradley, which are highly correlated data. You can see it for the Bradley data sets. In fact, the experimental errors were probably lower because we could predict this compound with much lower error, especially for low temperature range temperatures. And for patents, as for other drug-like compounds, there were a few compounds with experimental errors less than 50 degrees, and that's why here we have very high errors both for models and both for experimental accuracy predictions. But in general, for drug-like compounds, we got about the same 30 degrees, so we got again nice prediction accuracy for this data, and we could be able to predict new drug-like compounds with this accuracy about 30 degrees of precision. So what were outliers? We could look for compounds which were excluded. Some of them looked manually. We found that in some cases were polymers instead of monomers. Salts were, we excluded all salts, but sometimes compounds which were salts were just report without contrary on. Also could be possibly some text mining rotation errors, for example, melting point errors. People sometimes didn't put correctly values. Could be some problem with just this melting point, like different stereoisomers. But also we found that still compounds could have quite a number of pyrolysis instead of melting point data, since people not always put that compound did not melt but just degraded. In order to confirm this fact, we developed another model. We took data for pyrolysis, we took data for melting point, and we developed a classification model. So this was highly unbalanced set. We used specific tools for this handling, developed model, and this model was quite nice. It got about 80% of balanced accuracy for the whole data, so it could reasonably well separate pyrolysis and melting point data. Once we look for the pyrolysis against melting point data, again on the OCHEM website, it's also linked to the article, you could see that some specific groups were overrepresented in compounds which had pyrolysis. For example, phosphonic acid was very much overrepresented in this set of compounds. But some structural groups were more often in the compounds which had just a melting point. So there was really some separation between this pyrolysis and melting point compounds. Then we applied a model which was developed for classification to compounds which were outliers. We found that 22% of them were predicted as decomposing pyrolysis compounds, while only 14% were predicted for the remaining 223,000 compounds. So indeed, quite a number of compounds which were outlier were still polluted with pyrolysis compounds. That's why we have a problem with their prediction. Well, that's about melting point model, but the main interest in melting point is quite limited. It could be interesting only for respect of water solubility predictions. So there is a nice version developed by Jalkowski, which relate melting point and lipophilicity to solubility. We used melting point models, which was developed by previous work. It's been with NMine data mainly, to predict one of test sets, which produced by people with Hurston data set. 1300 compounds, we got 0.9 root mean square error, and model which was developed based on 275 types compounds improved this error quite significantly to 0.84. And the best model which have been published with the set when you have used the data for model development, so just not like here we used prediction of melting point and log P to predict water solubility, but when you just model the data, you can get something like 0.6. So we are still quite okay with the accuracy. It's not much worse than, and if this model can be applicable to very different chemicals, since it was developed with a very big data sets of melting point data, it can be very useful. Just coming to conclusions of my presentation. So what we have shown that basically automatic data mining approaches are very useful tools to process data, and what we found that basically text mining data, they have a similar quality to the manually created data. We could see this by predicting, making model on pattern dense, pattern data set, and predicting just other data sets. But also what we could have shown that we could develop models based on 100,000 compounds, and this model is basically available on the website. You can just go, you can see them. And of course, to work with such data, there are some challenges. You need to have appropriate system. You need to have quite a scalable system for CPU, memory, storage, and the final accuracy is about 32 degrees. While it looks quite a big one, it could be quite well suited to prediction of solubility of compounds. And still, I would say that another point, applicability domain of models should be taken into account once you apply a model, and this model, other models, to avoid some erroneous predictions. On this, I would like to finish my talk, and if I have still a few minutes, I can show you some online presentations about OCHEM. I don't know how Mark can tell us, and yes, I can just show it, or I can answer questions.
Let's see if there are any questions, if that's okay, Igor. Thank you very much indeed. One quick thing that would be great to do, maybe this is what you were going to do, can you just show us exactly where to find, the solubility model?
Exactly. So there is online OCHEM website, and you go to models. You can just go to apply a model. Apply a model. This is a menu. Okay. And here you can just look for solubility models. So there is number of models published, solubility. And you can see here, for example, what is solubility model based on log P and melting point. And this is a log PS model which was published by us in 2001. It's also made available, publicly available. It's also available on the website. So if you go just search for models, you can find them and you can apply this model for your compound. For example, I can draw a compound, yeah, whatever, and make predictions. You can just upload SDF file and also make predictions very easily. So it's just yeah, online going very well. Or you can also, if you would like, you can have also this software installed offline on your website in the company, for example.
In terms of, you mentioned there are several models there. Do you think there are one or two that people should focus on, or do you recommend running all of them and seeing what happens and what the consensus is between them? What do you think is the, if people want to use a solubility model, what would you recommend?
Well, I think I usually look for predictions by different models. So basically, deviation of models give you a degree of reliability of predictions. If different models agree, in this case, the chances to have good predictions are much higher. So I would say that basically I would use a few models, and for example, on the website we have 3 models for water solubility, and from this you can compare whether they provide similar predictions or not, and if yes, you can have much higher confidence that you are getting a good prediction.
Okay, and presumably also if people test the model against some experimental values that they have on some compounds from the same series, that would be helpful too when they get the chance.
Yes, exactly. They could test, for example, different models to see how the model performs, but it's also possible just to, if there are some experimental data available for a new series compound, it's possible to use this data to enhance model. So it's called a library model. You can add new data and you can enhance your predictions by adding experimental measurements for the given series compound. It's a different way. For example, I predicted for a compound with 3 different models, and you can see that, okay, quite for this compound, all models gave quite similar predictions, so it's quite a reliable prediction.
Okay, fantastic. Thank you very much. I think we must move on to Chris's presentation now on patent databases, I think. Chris? Excellent. Okay, thank you very much. Thank you, Igor. Let me change presenter. Excellent.
Okay, unmuted now. Right. Show my screen. Okay, how's that, Mark?
Yep, that's great. Thank you. If you could get a little closer to your microphone, that would probably be helpful.
Yeah, it's not the world's best mic. Oh, I see. Yeah, I can see the green green thing. That's not too bad, is it?
Nope.
Speak loudly.
Nope.
Good?
Nope.
Okay.
That's good. Thank you.
So, last thing I need to do is expand that screen.
Bottom right, next to the 117% sign.
It's tucked under that menu.
Ah, yes.
There you go. Right. Okay.
Perfect.
Thank you. Right. Let me get going. So you can see my pointer on the slides. Yeah.
Yes.
Right. I'm just going to run through some what I hope is interesting, and it's a kind of honest coverage of what's been actually quite amazing over the last few years, we've had a big bang in the exposure of open pattern chemistry. And I think actually part of what you just, one of the fruits of that open chemistry is exactly what you've seen in the large-scale property predictions from the previous presenter. So I'll just go through a bit of honest news about that automated chemistry extraction, chemical named entity recognition, and cover the major submitters in PubChem, and introduce a new, quite surprising initiative from WIPO, a bit of overlaps, and some of the caveats with automated extractions, and a bit of the roll your own stuff, yeah, and a bit about activity mappings and an MMV example to round off with. Okay, now in terms of general, I guess I have a bit of a professional reputation for looking at gift horses in one sense, that these are public databases. So not just patents, but it's important to, if you're going to get real utility out of a particular source, a database, typically you really want to know what's in it, yeah, and the statistics of entity relationship capture. And you can assess the comparative utility, and of course no database doesn't have caveats, overlaps, complexities, quirks and errors. But you can certainly, I'll show you a couple of things inside PubChem, you can ameliorate these by slicing and filtering. So you can overcome the worst, some of the worst issues. All public sources welcome feedback, but of course they may not have resources to implement these, certainly not at scale. Just for the record, in case you're interested, there's an example below where we looked at 4 horses at once, essentially, from the chemical structure and the protein content structure. Okay, so let's medicinal chemistry from patents. Now, I'm not going to touch on IP aspects here. For one reason, I'm not a car-carrying IP expert. I kind of get most of it, but it's quite a different theme. So I can address questions if anyone has them, but I'm going to hear from I'm taking it from the bioactivity angle here. So the patents, I think, historically very much have been a Cinderella source with underestimated utility by academics in particular. I think, well, the academics who don't file, of course. And as we know, I don't think any of us don't know, that you can see patents between 2 and 5 years or more before the paper with some of the examples, and they'll contain anywhere between twice as many or 10 times as many SAR data points than the eventual paper. And some of the findings from, we know are world-class medicinal chemistry teams, academic or commercial, this SAR will never appear anywhere else. More good news, paradoxically, the documentation is more open than patents. You don't have any restrictions for text mining or copyright or whatever. And in fact, despite some of the commercial providers banding around huge numbers, if you pass it all down, reduce the family redundancy, the ones that medicinal chemistry are interested about, CO7, A61, that's chemistry and biotechnology, is probably the corpus is well below 100,000 documents, so it really isn't very big. What people may not know is actually the examiner's search reports on the websites are public. They make quite interesting reading sometimes. They make some very criticisms on the inventorship, and they will record the prior art, of course, because that's their job. And added to that, you get in an application usually the citations of papers and patents are usually extensive. In fact, it's actually mandatory for a US application that you reference all the prior art you can. And of course, as we just heard, it's a massive synthetic protocol analytical data archive. Now, the interesting quirk, well, not a quirk, is probably this estimate actually comes from the company Accelera, used to be called GDK Bio, where their GoStar database includes just over 4 million chemicals extracted with patents with SAR mappings. So that's kind of a lower bound for bioactivity. So you can guess between 4 and 6 million. Now clearly it is a treasure trove for design, and we just heard about the large-scale chemistry property extraction. A bit of bad news here is there anybody unmuted? I can hear some rustling noises. Yeah. Can anyone else? Never mind. Right. It's more difficult to get stuff out in papers, and the access or the mining products historically have been dominated by the commercial domain. And of course, if you get into this in a big way, you've got to engage with the quirks of patent family redundancy, kind codes, A's, B's, B1s, B2s, patent classifications of several types, hundreds of pages of turgid legal text, and of course the markushness. And the major portals they tend to want to outdo each other with how many documents they've got in their pipelines. And this is certainly over at the WIPO, this is pushing towards 50 million. And of course, famously, some applicants violate the principle of patenting, which is full enablement, and they are guilty of various degrees of obfuscation to make our efforts to mine the data out more difficult. The minimal of which is the very helpful title of a novel compound in their applications. It's also important to realize, certainly from the IP point of view, that what gets into public databases is not patented structures, they're merely structures that have been extracted from patents. More bad news, finding the first filings can be difficult. It's certainly for the older drugs. It's important. The first filing is the invention, it is the filing of declaration of the novel structures, and in many cases the activity around that novel series. Judging the data quality, it's the same as the literature. It is a challenge. The data quality is not equal across the board. There are a few tricks like common authors, etc., and few journal authors actually cite their patents. In fact, it's not even formatted as a citation style in most reference managers. A large proportion of the SAR that does come out is unfortunately binned rather than discrete values. It's between 10 and 100 nanomolar or something. And a proportion of applicants don't actually declare their data values at all, but they will exemplify sometimes a very large series of structures. So there is some utility there. Now, for the public extractions which I'm going to talk about, the proportions of bioactivity is in fact fairly low. So as we've seen before, roughly about 5 million against an overhead of 15 million. That'll include a lot of non-medicinal chemistry extractions from the other patent classifications and a fair number of artifacts. And if you compare sources, you can see there is a constitutive divergence of extraction. So nobody appears to pull out the same stuff. Now, an automated extraction, for which we're very grateful for, has inadvertently contaminated the public database with a variety of artifactual structures, and some of these will run into the millions. CNER, this is the great, the big leap forward, actually introduced, credit to the IBM team under back in about 2011 under Steve Boyer and his gang, who started off the major pipelines here, but in a sense that was, the baton was passed to OCHEM later on, and now this is the Campbell. This is the outline, the schematic of the Campbell pipeline. So essentially you can look at the details, but it's documents in here, and the automated conversion of recognition of the semi-standardized RU-pack strings. As we know, there are several flavors of RU-pack string, but they put a toolbox together, and you essentially 4 operations: name to struct by lookup. It looks at atorvastatin up as a name and converts it, even if it's not there as RU-pack string. And of course, all the IUPAC names are translated. And then you have to have, of course, image to structure, I2S. And there's this fourth interesting quirk, which is the mol file actually drawn by hand under contract from the USPTO as part of their complex work unit program. And then they're fed into the processing system. And you'll use your system indexing, for example, abstract description claims. So, feed history into PubChem. Many people might not know that actually back in 2006, when Thomson Reuters Pharma first came online, it's a subscription database, so you can't get to their own outlinks, but they did deposit the structure. And a certain amount of, well, the key metadata was, of course, the date of which it went in. So, so they got up now to 4.3 million structures, about 40% patents. I suspect it's higher, but that's what they told me. So that would be about 1.45 million. Unfortunately, they stopped in this January. So I've been trying to tease them on Twitter and various other places to see if they'll restart it, but we'll see. And that was the IBM phase 1, where they made a bit of a song and dance about releasing it to the public domain. That was the 2.5 million. Then there was a very small effort from the EPO consortium, but that didn't produce much. And then we had this interesting effort from the, I forgot the name of the group now, but they're in Canada, where they made up the ScriptDB, okay, and they had 4 million compounds. But for various reasons, they probably won't run again. It wouldn't make much point. SureChem was the predecessor of, it was the commercial instantiation before it converted to Campbell, and their second release, I was involved in consulting with them at that time, a couple of years. Their second release got up to 9 million. And I'll show you quickly, there's a small but finely very well formed source from BindingDB where they do manual assay mapping. It's a modest number of compounds, but it's very, very interesting. Coming up to last year, we've got some uploads from the biggest CNER sources. Campbell hit 13 million and is continuing. IBM did a second phase, catching up, backfilling to 2010 patents, 7 million. And next move, they deposited their extractions of synthesis. So they're extracting synthesis, and this is the molecules that they got out in that process. So if you go to PubChem now, sum those sources and guesstimate, obviously it's 19.6, and you can guesstimate the extra Thompson set on top. So yeah, you've got some good news and bad news. Campbell is the major contribution to public chemistry. It's powerfully I'll have to speed up now and skip some of these points, leave you to read them on the slide share. So what you might not know is it's actually cross-indexing Unichem between PubChem and Campbell, so that's very useful. It's the only active CNER source. There are a few feed hiccups at the moment coming into Unichem and coming to PubChem. Now, CNER is compromised by poor OCR quality in WO documents and very dense image tables. So I'll cover some of the artifacts. Now, if you intersect at the CID level, you see corroboration, i.e. in the middle here of the Venn diagram. What is it? So it's about 6 million, where there's at least 2 sources agree, so that's kind of reassuring. But it's a little bit peculiar that these pipelines, script, almost 1 million, IBM nearly 2 million, so they get stuff that the other 2 don't. Okay. Now, Campbell will be larger because it continued. So this kind of opens up questions about CNER specificity. It's very important that you can, and a massive utility, you can intersect essentially the patents with the literature. And of course, for extracting from papers, Campbell is the de facto largest source, so that's now up to 1.5 million. 1.6 I think in 22. So as expected, you see quite a high overlap. And it also corroborates, because this is manual against the automated, so you get well, it's fairly modest in numbers, but you do get corroboration, and so you could pick up, you've got this crosstalk between published compounds and compounds extracted from patents. So this was interesting. I don't know whether anyone else knew about it, but I didn't, and this was that the WIPO, the International Patent Office produced a pipeline. This was in collaboration with InfoChem and NextMove. So you can now go to the WIPO site, the patent scope, and you need an account, and you can log in and do a chemistry search. So that's another free resource. CNER, the problem with automated extraction is it tends to produce shoulders of small stuff. Most of that small stuff is in fact split IUPAC strings. There are also some authentic intermediates there. Look at PubChem All. What you see here is the interesting, it's actually a vendor sweet spot, that little spike there. But if you look at a manual source like Thompson Pharma, and Campbell would be more or less the same distribution, you see that their extraction, they're choosing a discrete examples from patents, anywhere between 1 and 20 depending on the patent. This is the more medicinal chemistry distribution, peaking around there. And the small bits there, so that they are confounding in as much as that they do add a lot of noise. I'll skip the slide because it's a bit complicated, but many of the patents do not have associated bioactivity. Oh, this is just a fun slide. This on this side, ScriptDB, this is the famous now what's called Chessboard aim. It's a quirk where the CWU process, the contractors have been drawing tables into ChemDraw, and some of these came through as images, so you can see what's happened there. A lot of these big weird things in the other two automate they are actually legitimate and correct chemistry extracted from patents that are mainly not in medicinal chemistry. So that's it. Mixtures, a lot of mixtures coming through from patents, which are not terribly useful, so they're more confounding than they are useful. Even in Thompson here, you can see Thompson brought through a lot of combinations. They're arguably, some of them have IP significance, but the majority do not, so they are artifacts. But of course PubChem splits them and maps them back, so you can get hold of them. Another weakness of automated patent extraction is you get continual extraction of common chemistry. So if you go to the aspirin, so you will no less than 133,000 patent references, which are not much use. I'll skip that, but it's a nice artifact where you lost the punctuation and you've got a mixture through. Other forms of virtuals, which are kind of quirky, this was Shearing decided to exemplify all the stereo forms of this thing here. So you've got no less than 260 CIDs, stereo enumerations. I think these are virtual. I don't think they actually made them. Okay. The other thing that nobody made is deuteration. So you can see these enumerations. This is one of these Auspecs, one of these shotgun deuterating operations that were filing like crazy in about 2009. There's a slide set here. So you see here 986 deuterated CIDs. Now I think about 4 of them were actually made. Now there's some interesting good news. It's not associated with, in a sense, CNEIs. If you either got an unprocessed document, i.e. it comes out on the day of publication, or if some of the examples that you find there's clearly lots of gaps, things missing, you can use a set of free tools, which I've used. This is chemicalize.org, which is now got a revamp, and you will have to sign in. there's the there's Daniel Lowe's Opsin that he wrote at Cambridge University. Daniel's now at Next Move, and you got the famous Ultra. That was offline for about 3 months, but due to US government firewall issues, but now it's back on. So that's you usually have to correct it, but it can be very useful. A couple of bits of good news to round off. In as much as if you go to binding DB, I can't go into all the good details, but they've used the mol files from the CW to curate activities from patents. So they've got target, manual expert target mapping. So it's well worth a look, and you'll open these up. These are not all compounds, but they're compounds times activities. So if there's multiple targets, you'll get multiple sets. But it is very, 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 very useful. So you'll another one, which is, this happens to be us. So this is home territory for me. Now we have a very modest amount of patent connectivity. There are two things we do. We will, during curation, we will often cross-check to see if there's been a filing. To see if there's a good SAR data set in for example, Campbell, and we'll point to it. The other thing is there are a couple of instances where actually we find targets are patent only. Now this is one case which is actually base 2. A lot of interesting stories about base 2, and there's something very interesting, slightly peculiar in this set of compounds. The compound at number 2. We'll see if anyone can guess what the issue is in the questions. I shall finish with an example from Medicines for Malaria. It's just kind of a utility example. I can search with them as applicant in Campbell. I'll find one of their patents. This one was from 2015. I don't think they brought I don't think there's a paper out on this yet. Okay, so this is in advance, and you've got a nice SAR table. You can pick up example 1 and walk through into PubChem, and because of Campbell's have done such a good job, you can see all the examples nicely clustered. But if there's a couple of clues here. If you have a discontinuous number, it may be a structure related from another source. For example, one of these had a beta-kinase inhibitor nested in. So you can do this kind of stuff, and you can walk from patent to patent. Okay, so the Big Bang massively outweighs caveats. It's a very nice horse. Most exemplifications are now out there. The contributing sources to be congratulated, especially PubChem for wrangling them. And it's important to look closely at the gift horse. There's a lot of enabling for those who can't afford commercial sources, but anyone using commercial sources now has to synergize with these open ones. And I'll leave this slide up for the questions. Thank you very much.
Great. Thank you very much indeed, Chris. I'm just looking to see if you do have questions, just raise your hand on the interface or type in a question. I had one question, Chris, and that was, what's the kind of, you mentioned a few different databases, you know, binding DB, your own, Campbell, PubChem. Where would you go first? And you know, if you've got a compound and you're kind of thinking, well, what's in the patent literature associated with this?
If you've got a compound, you go straight to PubChem, okay?
Mm-hmm.
And then you'll see under substances, you'll see all the sources that have submitted it. If you see Campbell, I would click on that straight off because you'll go straight through. You may see binding DB as well. Okay, so you go through to there. You'll see us in the relatively few instances. And if you don't see anything, it's probably worth checking at the moment. Check Shaw-Campbell in situ, because there's probably, it looks like there's a 6-month lag at the moment. Okay, so you can check the updates on what they pulled out very recently. So yeah, go to PubChem, look at the sources, and if there's a Shaw-Campbell link, click that first. That'll take you through to the patent extraction. Now, PubChem, there is a caveat. PubChem indexes patent numbers, but they're a bit mixed up. Then they automatically parse them from the USPTO. So probably don't go on those links first, but you can see those later.
Fabulous. Okay, thank you. Any other questions?
I had a quick question about OSRA. I hadn't come across that at all before. So you can use that to translate the pictures and the patterns into electronic readable structures, can you?
Absolutely. Well, that's what they, the pipelines, I think, or there's a couple of, OSRA and Clyde are well known. Clyde's not, but OSRA has a public interface and is a public code base. Mm-hmm. So you can install that on your end. But I use the web interface. It's quite useful. As in, whatever, about 7 times out of 10 you will have to correct, but it's relatively trivial. So you correct it and then take it to the PubChem interface and pop it. That's what you. So that's what you can do.
That's fabulous. I can think of lots of uses for that.
Yeah.
Brilliant. Thank you very much indeed, Chris. I can see we're just on the hour, so I'm going to suggest we stop there, but that's very, very helpful. Thank you to both Chris and to Igor and to Caroline for setting up this session. And we have another one of these in 2 weeks' time where we will be talking about a PK tool. You have had an email because if you found your way to this, you've been invited to the other one too. But it'd be great to see you there to talk about a free analysis and prediction tool for PK. Thanks again to Chris and Igor, and hope to see you next time. Cheers, bye.